Very quick review here of what we learned yesterday. The biggest thing that came out of it, and this is not what we started off with, but the biggest thing that came out of it is your ability to translate an expression that's in logarithmic form, or an equation that's in logarithmic form, I should say, to an equation that's in exponential form. But we started off by talking about inverses, and these two things are not the same. Y equals 2 to the x is not the same as x equals 2 to the y. They are inverses of each other. So if you know what the graph of y equals 2 to the x looks like, you can figure out what the graph of x equals 2 to the y looks like by going through that process we went through yesterday of taking points and switching x and y coordinates, or by reflecting all the points of y equals 2 to the x across the line y equals x, because that's how inverses are created. Similarly, or along the same lines, if you know the properties of y equals 2 to the x, which you should, that's where we started the unit. For example, you know that the line y equals 0 is a horizontal asymptote on y equals 2 to the x. Then, since x equals 2 to the y is the inverse, that means instead of having a horizontal asymptote, you'll have a vertical asymptote. And instead of it being at y equals 0, it will be at x equals 0. If you know the domain and range of y equals 2 to the x, then you can figure out the domain and range of x equals 2 to the y. For example, and I'll write this down this time. If you know that for this function x is any real number, then you know that for this function y is any real number, because you're switching x and y, so the properties of x and the properties of y switch. If you know that for this exponential function, the range is y is greater than 0, then that tells you that the domain of this will be x is greater than 0. So that's where we started off. But as I said, the most important thing that came out of yesterday is your ability to understand that x equals 2 to the y is equivalent to writing y equals log base 2 of x. And it doesn't have to be x's and y's. It could be anything. It doesn't have to be even in the context of a function that's logarithmic or a function that's exponential. If I have p equals log base q of r, then that means q to the p equals r. And as I said yesterday, the logarithm is an exponent. So this thing is an exponent. It's equal to p. That means p is the exponent. And when you see something like, well, we can just go to some examples here. I don't believe 4 was assigned for some reason. Maybe because I just think it's too elementary, but this should be obvious. If I say to you, what is log base 5 of 125, you should say it's 3, because 3 is the exponent to which you raise 5 to get 125. And the logarithm is the exponent. So the logarithm equals the exponent. That's a quick summary of what we did yesterday in a nutshell. Take a moment and look over your work and see if you have any questions. Lynette, fire away.
Question 13.
13? So evaluate each expression. Now this can get... Logarithms are interesting because if you just happen to look at something in the right way, it becomes easy. One of the things I've told you is that when you're looking at a logarithm, and I understand you're not asked to find this logarithm in this question. And yesterday I said when you're trying to find a logarithm, put it in exponential form to make it more understandable. Well, before we try to decipher this question, my advice to everybody is when you see this in an equation, take a minute and write it in exponential form, because there might be some information in that translation that's more valuable than the logarithmic one. And in fact, the information in that translation is the answer to the question. You're asked, what is 5 to the m? Well, it's 7. And if you don't make that translation, I can easily see how you could get kind of trapped in a vortex here of trying to wrap your head around what it's asking. But it just turns out that if you write that logarithmic expression in exponential form, it's 5 to the m equals 7. You were asked, what is 5 to the m? It's 7. And there's going to be a level of frustration in this unit as we get deeper into logarithms because of this, because of the different appearances that things can take on and the different paths you can take. It's almost like trigonometry, but it's a little bit different in that respect. Does that make sense, Lynette? Okay, and you would do B in the exact same way. Any other questions? Yeah.
14.
Yeah, let's look at 14. So 14 is starting to ramp it up. When you have embedded brackets in mathematics, if I had the following, if I had 2 plus 6 squared times 4 I was going to put square root, but I don't want to put a symbol here. I want another set of brackets. I'll just go plus 1. Okay? And I said to you, evaluate that. When you have embedded brackets, when we say you do brackets before anything else, there's an implication there that you do the inner brackets first. So we would start off in this question doing the green set of brackets. Then we would do the red set of brackets. Then we would do the black set of brackets. And then we could add 1. So you start in the middle and work your way out. So what I would do here to begin with, Janessa, is I would take 2 plus 6. And now what I have is 8 squared in its own set of brackets. And that's going to be times 4 in its own set of brackets plus 1. So now I can figure out what 8 squared is, because that's the next set of brackets. And I get 64. And that's in its own set of brackets times 4. I think I put plus 4 there. It should be plus 1. And then you can go 4 times 64, which I think is 256. Did it again. And then you can go 4 times 64, which is 256. Then you can add 1, it's 257. The lesson is you start in the inner brackets. So it doesn't matter which one I take. I'm going to pick on A. And this says we want to take the base 2 logarithm of the base 3 logarithm of the base 4 logarithm of 64. So we're going to start on the inside, and we're going to say, what is the base 4 logarithm of 64? And even though we just started this yesterday, everybody needs to be at this point now. This is saying, to what do you raise 4 to get 64? If log base 4 of 64 is confusing to you and you don't even have any idea what it means, then you need to go back and review yesterday's lesson. Log base 64 means the exponent to which you raise 4 to get 64. I mean, I can write that. This is what's going on in our head is this. But I don't know that you need to write that every time. That's a question mark. And the answer is 3. With a little bit of plunking around on your calculator, 4 to the 3 is 64. Or in your brain, 4 to the 3 is 64. So that's 3. Now what we have is log base 2 of the log base 3 of 3. Or the base 3 logarithm of 3. I have heard online in many videos, YouTube videos, and I hear people saying log 3 of 3. I think that's wrong. I don't think you should be saying log 3 of 3. You need to be saying the base 3 logarithm of 3 or log base 3 of 3. I think that word base is important. Maybe it's not wrong. It's sloppy. It's lazy. So log base 3 of 3 is the exponent to which we raise that base 3 to get 3. Well, you raise 3 to the 1 to get 3. And that means that now this is log base 2 of 1, because log base 3 of 3 is 1. And I don't even need the brackets anymore, really. Log base 2 of 1 is saying, to what do I raise 2 to get 1? The answer is 0. 2 to the 1 is 0. So this works out to be 0. If we were to quickly run through B here, log base 10. Another thing that's kind of sloppy, this is base 10. And I admit I do this at times. I would write that, but that's really, I think this is important. It's implied, but it's going to be important particularly for tomorrow's lesson. So log, it's base 10 because it just says log. Log base 10 of 10 to the 16 is 16. It's saying, what do you raise 10 to so that it becomes 10 to the 16? Well, you have to raise it to the 16 to get 10 to the 16. So this is 16. Now this becomes log base 4 of log base 2 of 16. Well, what is log base 2 of 16? It's the exponent to which I raise the base of 2 to get 16. 2 to the 4 gives me 16. So this is 4. So now I have log base 4 of 4, which is 1. Because 1 is the exponent to which you raise 4 to get 4. Is that good? Okay. Other questions? Janessa.
9.
Okay. So we want to determine the equation of the inverse. Then we want to graph it. I don't know that we need to graph a detailed graph of it, but we'll sketch it. Okay. The equation of the inverse. Well, if we start off with y equals log base 1/4 of x, and we want the inverse is going to be found by swapping x and y. Right? That's what we do. But the issue here is we don't want any function in terms of graphs and equations written as x equals. We want it written as y equals. So how can we write this as y equals? Well, we can change from logarithmic to exponential form. And get, I just want to do one thing here before I move on. And get 1/4 raised to the x equals y. And I changed the colors because I want to impress on you that the thing I've written in brown is not the same as the thing I've written in red. They're inverses of each other. They're different. But the two things I wrote in red are the same thing. They're just written in a different language. You should know from the first unit that function we're looking at, that function we are looking at fits the mold of y equals c to the x, where c is a number between 0 and 1, which is 1/4, and that means it's a decreasing function with a y-intercept of 1. This is what the graph looks like. You can answer the rest of the problem now talking about the domain, the range, the equation of the asymptote, which will be the x-axis, and we're done. Okay. Other questions? Yeah.
24.
Thank you. Now, this is just for my own knowledge. I assigned 24, didn't I? Okay. I would be surprised if nobody asked about 24, because if nobody asked about 24, my guess would be none of you tried it. Or not all of you tried it. Okay. It's not a simple question. So 24 gives you m is equal to log base 2 of n, and 2m plus 1 is log base 2 of 16n. What's m and n? So what we have here is a system of equations. It's just that You know, when you solve a system of equations, normally you do stuff like elimination a lot of the time. Well, elimination is not going to work here. Substitution is going to be the line of attack. But along the lines of what I mentioned earlier, when I see m equals log base 2 of n, why don't I just write down what that is in exponential form? That means that m is the exponent on 2 that gives you n. And one of the things I notice is this second equation that I have here is one where if I took this expression and I put it in here, then I would get a single equation with only m's. Right? Let's not worry about how we're going to find m just yet. Getting rid of a variable in an equation is a huge step forward in solving a system of equations. So we end up with 2m plus 1 is equal to log base 2 of 16 times 2 to the m. Now, there are a couple of ways we can proceed from here. I think we should just put it into an exponential form. And what we end up with is 2, that base, raised to what the logarithm is equal to 16 times 2 to the m. And I will tell you right now that we have turned this equation or this question into a problem from Monday, where we learned how to solve exponential equations that contained a common base. Can I write 16 in base 2? Sure. So that's what I'm going to do now. I'm going to write everything in base 2. I get 2 to the 2m plus 1 equals 2 raised to the 4 times 2 raised to the m. I know from grade 8 and 9 math, and continuing on after that, that when I multiply a common base like I'm doing on the right-hand side, I add the exponents and I keep the base the same. Right? X squared times x to the 4 gives you x to the 6. We add the exponents. So now what I have is 2 raised to the 2m plus 1 equals 2 raised to the 4 plus m. And now, since the bases are the same and the powers are equal, the exponents must be equal. And at this point in time, it's just a matter of solving this. If I subtract 1 from both sides, I get 3 on the right. If I subtract m from both sides, I get m equals 3. We're not done, because don't forget we have to find the value of m and we have to find the value of n. But there are a number of different relationships between m and n floating around here. I mean, I would say to you that this is the relationship that will be our most direct path to finding n. We can put in m equals, did we just get 3? We can put m equals 3, so you'll get 2 to the 3 for n. By the way, just to polish this off before we get started today, you're going to get n equals 2 to the 3. I can't tell you how many times people end up writing something like 9 there. You just look at it and go, oh, well, it's 9. 2 raised to the 3 is 2 times 2 times 2, which is actually 8. 3 raised to the 2 is 9. 2 raised to the 3 is 8. You know, try to avoid those, what we call silly mistakes. All right, any other questions before we get started today? Okay. If you have further questions, we can go over them later. We're going to move on today, and well, this is called transformations of logarithmic functions, but there are going to be a number of other things we learn along the way. One of them is to solve problems that are applications of logarithmic functions. Now, the nice thing from a student's perspective is when we solve problems that are applications of exponential functions, sometimes you have to come up with the equation. You don't for logarithmic. There's no template for understanding where a logarithmic application equation comes from. And we're also going to be using something called the change of base formula to solve problems. So in the following examples, we're just going to use our knowledge of transformations. The first question says, sketch the graph of log base 3 of x plus 9 plus 2. And that's it. We have to be able to sketch it without using a graphing calculator. And what you need to understand here, this is tricky, okay? The function we are after is a transformation of y equals log base 3 of x. We are after this function, log base 3 of x plus 9 plus 2. So everybody should know that the function that's on the left of the screen simply needs to be translated 9 units to the left and 2 units up. That's easy. But the problem is, what does log base 3 of x look like? And I'm going to suggest to you that you're not going to finish this course and know what log base 3 of x looks like precisely all the time. If you do, that's great, but then you also have to know what log base 2 of x looks like, and log base 10 of x, and they are slightly different. So how you come up with what this looks like is you understand that it's the inverse of y equals 3 to the x. So in order to get the logarithmic function that we are going to transform, you're going to start off by looking at the exponential function and transforming it. Now, I don't think anybody here uses pen. I have some students in my grade 11 class that use pen, and it just drives me nuts. You're probably going to put some points down in what I show you and then erase them later, because I don't think it's a good idea to put this graph on the grid, y equals 3 to the x, the logarithmic function on the grid, and our answer on the grid. So I'm going to use a particular color for y equals 3 to the x, and then I'm going to erase that. Okay? So what does y equals 3 to the x look like? Y equals 3 to the x has a y-intercept of 1, and when we go over 1, we triple. And when we go back 1, we divide by 3. This is a very rough idea of what 3 to the x looks like. And I'm going to put in an asymptote just so you can see it, but I'm going to get rid of the asymptote very shortly because I don't want too much cluttering our workspace. What 3 to the x looks like is this. And again, I'm going to erase all this. Y equals log base 3 of x is the inverse of that. Okay? And if you want, you can now sketch y equals log base 3 of x, but you don't even have to sketch that if you don't want to. The inverse of this is going to have a vertical asymptote. It will have an x-intercept of 1. And instead of, this is tricky, but instead of for the exponential where we go to the right 1 and then we triple, here we're going to go up 1 and triple horizontally. So that means this will be a point. 1 times, whoops. We go up another 1 and we triple 3 to get 9. So what this logarithmic function looks like, and we can go back, down 1 and into a third. What this logarithmic function looks like is this. This is log base 3 of x. So all this work that we did is done solely to determine the function that we're going to shift 9 to the left and 2 up. Okay? So when we shift this 9 to the left, that asymptote is going to be 9 to the left. Every point is going to be moved 9 to the left and 2 up. So this point right here is going to be moved 9 to the left, which will put it here, and 2 up. This point right here is going to be shifted 1, 2, 3, 4, 5, 6, 7, 8, 9 to the left, and 2 up. And we've talked about this before with exponential functions. Once you kind of have one of those brown points there, you have the rest of them because the rest of them are in positions relative to the point that you started off with. So we're going to have a point over here, one below and third. We're going to have another point that is 3 times further away from that asymptote than this one, which will be here. So what our logarithmic function will look like is that. I don't really have a high level of confidence that you would be asked to do this on an exam. We're learning about the properties of logarithmic transformations by doing this. Now, we are asked to do some other things. What's the equation of the asymptote? Well, the equation of the asymptote is x equals -9. If you stop and think about it, it's because h is -9. The asymptote for a logarithmic function starts at x equals 0, so any horizontal translation moves it. What are the domain and range? Well, you can see that the range is any real number. The graph extends up and down forever. The domain is x is greater than -9, because that's h. Could you ever have a logarithmic function where x is going to be less than h? Could we ever take this bluish graph and transform it? We could even use h equals -9 and transform it so that x would be less than -9. What would have to happen here, Ariana? Right, a horizontal reflection would have to occur. So if there was a b value that was negative, you'd be done. Now, let's take a look at the rest of this. Y-intercepts, if it exists. Well, the y-intercept is right there. We can see it, right? But let's do it algebraically. We have this equation, y equals log base 3 of x plus 9 plus 2. Am I right? Did I write it down correctly? Okay, so when you find a y-intercept is where x equals 0. So let's put 0 into this equation. Y equals log base 3 of 0 plus 9 plus 2. Well, that's y equals log base 3 of 9 plus 2. And that plus 2 is not 9 plus 2. Okay. Log base 3 of 9 is 2, isn't it? Log base 3 of 9 is the exponent to which you raise 3 to get 9. That's 2. So the y-intercept is 2 plus 2, which is 4. And if you look at your graph, that's where the point was, wasn't it? Okay. Well, what about the x-intercept? The x-intercept is where y equals 0. Now take a look at the x-intercept here. I didn't do a stellar job of graphing this. Let me see if I can tweak this a little bit. I'd be better off just redrawing it. Look at where that x-intercept is. It's very close to that asymptote at -9, but you can't read it from the graph. So keep that in mind as we go through and we solve this equation. We're changing y to 0. So what would we have to do first? Well, we would have to move the 2 to the other side. We would subtract 2 from both sides. Now what? See, some people would say, now we're rearranging further. But I would say, when you get to the point where you have a logarithm equals something, you're just translating it to the other language. That's the rearrangement. And we're going to get 3 to the -2 equals x plus 9. And that means x is equal to 3 to the -2 minus 9, which is 1/9 minus 9. I mean, you can grab your calculator here. Do that for me. Grab your calculator and get negative, I want to say -80 ninths. And in decimal form, what was that? 8.8 repeating? 9.8 repeating? 8.8 repeating. So negative 8.8 repeating is the x-intercept. Example 2, we're going to do the same thing. I'm going to start off, though, by simply sketching y equals log base 2 of x without starting with y equals 2 raised to the x and doing the inverse. You should get a little more familiar with the fact that these logarithmic functions, if the base is greater than 1, will have that asymptote and that x-intercept, and they will have, please don't draw this, but they will have this general shape. Yes? Very sloppy, but that's the shape they're going to have. What are the more precise features of it? Well, since the base is 2, every time you go up 1, you double. You go up another 1, you double. Up another 1, you double. It's the opposite of what's going on with exponential, where you go to the right 1 and you double up. Here we're going up 1 and we're doubling right. So what log base 2 of x looks like is this. This is not the function we are after. I hope you can see that there is an a value in this, there is a b value in this, and there is an h value in this, in terms of going from log base 2 of x to that function. Can everybody take a moment and write down what a is equal to, what b is equal to, and what h is equal to? A is negative 1. So that's going to involve a vertical reflection. B is 2. Darius, can you tell us what h is? Positive or negative? Will be negative because I'm glad you didn't say 6, by the way. Right? We have to factor out that 2, but remember that it's always x minus h. So h is negative 3. We have done these transformations so many times, I'm not going to write them down, I'm just going to say them verbally. There's a vertical reflection. There is a horizontal stretch by a factor of 1/2, and then we shift things 3 to the left. In the end, will a vertical reflection change that asymptote? No. Will a horizontal stretch change the asymptote? No. In the end, the asymptote is going to be over here at negative 3, because whatever happens, everything in the end is shifted 3 to the left. So I'll do this one in red. I'm going to take this key point here. And don't forget, I'm going to leave the asymptote there. I will draw in a new asymptote for the new function. The new asymptote is here. I'm going to take that point and reflect it vertically. It doesn't move. I'm going to stretch it horizontally by a factor of 1/2, which means it will be at 1/2. And then I have to shift it 3 to the left. Notice that this point right now is 1/2 away from the asymptote. When I shift it 3 to the left, it's going to land 1/2 away from the asymptote. If I take this as a key point and I reflect it vertically, it ends up being here. I stretch it horizontally by 1/2, it ends up being here, which currently is 1 away from the asymptote that we're starting with. If I shift it 3 to the left, it's going to be 1 away from that asymptote. I don't think we need to do every point. Let's do one more, and then we can get a rough picture. I'm going to take this key point, reflect it vertically, stretch it horizontally by a factor of 1/2, shift it 1, 2, 3 to the left. What our graph looks like is that. Equation of the asymptote, x equals -3. Domain, x is greater than -3. Range, y is any real number. I might call on you for your help here. I'm pretty sure I know that this is correct, but can you enlighten me? Okay, so a y-intercept is where x equals 0, negative log, except there's a base there, isn't it? Base 2? Log base 2 of 2 times 0 plus 6. So the y-intercept is the negative logarithm base 2 logarithm of 6. Some number. Let's just leave that alone for the time being. The x-intercept, even though we can read it on the graph, is where we change y to 0. I'm going to get rid of this negative first. There's a couple of ways to do it. I could move the logarithm term to the other side where it becomes positive. I could divide both sides by -1. I could multiply both sides by -1. We end up with log base 2 of 2x plus 6 equals 0. Put it in exponential form. 2 to the 0 is 1. Subtract 6 from both sides to get 2x equals -5, which leaves us at x equals -5 over 2. And if you look at your graph, you will see the x-intercept is at -2.5. Now, what about this? Let's try to figure out what log base 2 of 6 is. It is the exponent to which you raise 2 to get 6. So 2 to the 2 is 4. Well, that's not 6. 2 to the 3 is 8. I almost wrote 9. 2 to the 3 is 8. That's not 6. 6 lies between 4 and 8, which means that this number, log base 2 of 6, is a number that's between. It's a number, let's write it this way, that's between 2 and 3. That's all we know, okay? The y-intercept is a number between -2 and -3. And you can see that, can't you? By the way, does your handout have a -2 here? I just noticed that. That is a typing mistake on my part. That should be a -4. I'll have to make a note of that and change it in my notes. So the y-intercept is between -2 and 3. We'll come back to that a little bit later. Let's move on now. Example 3. In each case, the red graph is a transformation of the blue graph. And I typed out red graph and blue graph on your handout because you don't have colors on that handout. So that means that the blue graph is the original. Okay? The red graph is a transformation of the blue graph. Well, if you take a look at the red graph and the red graph is pushed more towards the y-axis. Can somebody tell me why? There's a couple of reasons for this. Why we can't say that the blue graph is simply translated to the left. We can even count these spaces. This is 3 spaces in here. Why would saying, let's translate the blue graph to the left 3 places be wrong? Miles.
It's not like the line doesn't move?
Right, the asymptote doesn't move, yeah. So the fact that it's kind of implied here, looking at the red graph's curve right in this region, that it's still asymptotic at that point. So the only explanation here is a horizontal stretch. And to go from where that blue point is here to where this red point is involves a stretch by a factor of a quarter. The blue point is 4 away from that asymptote or axis. The red point is only 1 away, which means we're dealing here with a horizontal stretch by a factor of a quarter, which means B is 4. So we're going from this, which is the blue graph, to y equals log base 4 of 4x. I hope it's clear looking at going from the blue to the red graph here that there is a vertical reflection. In fact, I would argue to you, well, I wouldn't argue, that's the wrong word. I would say to you that you should be able to come up with the concept that A is -3 without knowing anything about logarithms. If I just gave you those two graphs and I said, what is the value of A? You would say A is negative because there's a vertical reflection, and that point, that blue point, if we reflect it vertically and then stretch it vertically by a factor of 3, will take us to the new point, which means the new function is y equals -3 log base 4 of x. Any questions with B? All right. Determine the domain of this graph. So the fact that they're telling you the base is between 0 and 1 is what your English teacher would call a red herring. It's just there to take you off the track of doing your work. It's not important. What's important is the argument must be greater than 0. Always for a logarithm. You can't take the logarithm of a negative or of 0. There is a way to determine the domain here by graphing this function and looking at where the asymptote lands and looking at what the graph looks like. And we can certainly do that in a minute. But I'm simply going to solve this. This is 3x is greater than -12, which means x is greater than -4. That's the domain. That's it. If you want to take a transformative approach, meaning transformations, log base who cares what, 3x plus 4, when we factor that 3 out, we can see that h is -4, which means the asymptote will be shifted 4 to the left and land at x equals -4, and the function is to the right of it. So x is greater than -4. Now, we want to rank these logarithms in order from smallest to greatest. And I'm going to teach this a different way this year. Ignore that change of base formula which is on the right for a second. There is a way we could do it by trying to reason out, well, 6 raised to the 2 is 36, 6 raised to the 1 is 6, so log base 6 of 24 must be between 1 and 6. But that's not good enough. We want to evaluate what this is. So I'm going to teach to the masses right now, and there will be 1 or 2 of you that are going to lose out here because you do not have a TI-84 calculator or higher. You have a TI-83. And I would highly recommend getting your hands on a TI-84 for this exam and for the diploma exam, just to borrow it from somebody. Okay? The math department has some. You can speak to the math department head about that, Mrs. Russell, and maybe she can set you up. On your calculator, and Will discovered this yesterday, or he knew it yesterday anyway, if you go to math and you scroll down enough, or just scroll up and it'll take you to the bottom, there is something called log base. Now, I want everybody to choose log base and put up your hand if you see on your screen what I'm looking at on mine. Is anybody seeing the exact same thing? That's good, okay? Because that means that you're in a mode that I really don't like to be in. You're in this math print mode. And I don't like this for a number of reasons. One is when I raise something to an exponent, I always forget to move the arrow back down. The other is if I type a long function, it goes off the screen, which I think is poor design for learning, because then you can't look at it. But anyway, as long as you're in that mode and you go to your math menu and choose log base, a pretty beautiful thing happens. And now my next question for you is there anybody who has a TI-84 or higher and you're not seeing that? Because there are different operating systems, and if you're not seeing it, then we can change the operating system on your calculator so you do. Okay. So if I want to know what log base 6 of 24 is, I just do this. That's it. Going back over here to our x-intercept, you remember I said let's just leave that alone? Or our y-intercept, rather? We can figure out what that is. -2, we said it was between -2 and -3, because log base 2 of 6 is between 2 and 3. I'm just going to scroll up and grab this. Log base 2 of 6. Oh, it's -2.58. So we can go through with this question and calculate these four things. This was 1.77, approximately. Log base 3 of 66. Is approximately 3.81. Log base 10 of 3. Well, I can just go log of 3. I don't need to get fancy here. Log is base 10. I could go log base 10 of 3. It's 0.47. And log base 20 of 5. Is about 0.54. And so ranking them from smallest to greatest would be log base 10 of 3, followed by log base 20 of 5, followed by log base 6 of 24, and then log base 3 of 66. And if this were a numerical response question, which I don't even know that it would rise to that level, you would have these labeled as 1, 2, 3, and 4, and you would enter the digits in your 4 boxes. If you do not have that feature, then it is possible, and this formula is on your formula sheet, it is possible to calculate non-common base logarithms using the change of base formula. This is saying if you have a base b logarithm of an argument and it's not base 10, and you want to change it to base 10, or any base, you can use a new base, and the logarithm on the top is the old argument, and the logarithm on the bottom is the old base. Which means, for example, log base 3 of 66 is log base 10 of 66 over log base 10 of 3. And you will get that 3.81. We don't need to worry about why it works. The thing, you may wonder, what am I doing different? What I'm telling you is, I believe, and I would never have said this in the past, but I've changed, that I think if you have that feature on your graphing calculator, you don't even really need to worry about the change of base formula. It might come in handy in calculus, okay? But otherwise we wouldn't use it. All right, any questions with the change of base formula or calculating those alternate base logarithms? As I said, if you're working with a TI-83, this feature alone is worth the price of admission of a TI-84 calculator or higher. I'm not saying go out and buy one. See if you can get your hands on one. Okay. All right. we're going to do a couple of quick examples. I told you at the beginning that we would do applications of logarithmic functions. I'm going to write out this equation. S equals 7 times the negative of the logarithm of t divided by 3 plus 1. I have no idea why often in welding manuals and textbooks they have it written this way. There must be some physical reason. But 7 times negative 1 times the logarithm of t is negative 7 log t. Please make a note that this is a base 10 logarithm. What is this about? Most welding helmets have electronic shields now. They work on the principle of polarization, but some welders still use what's called a welder's glass. They typically use a number 14 welder's glass. And if you want to look at an eclipse, you could look through a number 14 welder's glass, and it blocks out so much of the damaging light. I mean, you don't look at the sun unless you're an idiot, or unless you want to lose your eyesight and permanently have blank spots in your vision. But a number 14 welder's glass will block out a huge, huge amount of light. And what we're going to determine is the proportion of light it blocks out. So in this formula, S is the shade number, and T is the proportion of light that it allows. So if you end up with T equals 0.3333, it's only allowing 1/3 of the light through, because that's 33%. And the question is really this. What's T if S is 14? That's what it is. And this is not a complicated question. We're simply going to solve this equation. Negative 7 log of t, and it's a base 10 logarithm, over 3 plus 1. And I would say to you that rearranging this equation for log of t is grade 9 math. We have to subtract 1 from both sides to get 13 equals negative 7 log of t over 3. We have to multiply both sides by 3. I'm just going to show this, although I don't think you really need to, and get 39 equals negative 7 log t. And then we can divide both sides by negative 7. We're just rearranging by getting rid of coefficients and constants. And you end up with log of t, the proportion of light that it allows through, equals 39 over negative 7, which is some number. Now the question is, how do we peel off that log? How do we go from log of t equals a number to t equals a number? And this is the thing, I see people watch people write exams, and they do all this work, and then they're at an impasse here. Thomas, do you know? Yeah. This is a base 10, so take my advice. If you don't understand what the next step is, write it in exponential form. How many of you are in Chem 30 right now? Are you already on to pH? Are you learning pH? Have you learned that the hydronium ion concentration is the antilog of the negative pH? Okay, never mind that. So we're simply going to write 10 raised to the negative 39 over 7 equals t. That will be our answer. Interestingly enough, if you look at your log key, which is a base 10 logarithm, and you look at the second function of it, it says 10 raised to. Because 10 raised to x is the inverse of log base 10 of x. Anyway, I don't typically do that. I just say 10 raised to bracket negative 39 over 7. I get that number. Wow. I get 0.00000068. That's the proportion of light that it allows through. That's not a percent. I'd have to multiply that by 100 to get a percent. But if I did that, it's like 0.00068%. It's such a tiny amount of light that goes through. That's the answer to the question, though. Let's do one more. The first time I saw this, I thought somebody's having me on here. Somebody's pulling my leg, as my dad would say. It says there's a logarithmic relationship between butterflies and flowers. In one study, scientists found that the relationship between the number of different flower species that butterflies feed on and the number of butterflies they observe in that region is modeled by a function that's logarithmic. It says the number of species of flowers is equal to negative 2.641 plus 8.958 times the base 10 logarithm of how many butterflies they observe. And I really did. I thought, okay, well, I've been there. I've made up exam questions where I just kind of make something up because it's a word problem. And I try not to do that anymore. I try to go online and find things that are real. Well, after I saw this, and this was a few years ago, I looked up online the study. This is the data. This is the actual data. And it's all, I mean, I hope you understand, nature very rarely follows a mathematical formula exactly, right? Because they're unaccounted for variables. My cat goes into the garden and eats a bunch of butterflies. Okay, that could be something that the study is not taking into account. But it's pretty darn close. So the question here is, how many butterflies should we observe if there are 25 flower species? That's what we're asked to do. We put 25 in for F, and that's equal to negative 2.641 plus 8.958 log of B. Now, I just want to pause for a second here and have everybody look up here. If I gave you this equation, finding x is childlike, isn't it? At this level? Okay. So you would rearrange this by adding 2.641 and dividing by 8.958. Well, you're going to do the same thing, but you're not going to get x, you're going to get log of b. And I'm going to give everybody a minute, well, 10 or 15 seconds, to calculate what log of b will be equal to. And it's okay to put it in a decimal form. And the decimal answer you get is going to be very close to 3. I don't know whether it's 2 point something or 3 point something, but Will, do you have a decimal number? 3.09. And what you would do is take 25, you would add the 2.641 to get 27.641, and then you divide by the 8.958. And then again, since this is a base 10, we can write this as 10 raised to that number of, did you say, can you repeat it please? 3.09. I'm assuming there were more decimals. Yeah. But you would carry all your decimals. Well, 10 to the 3 is 1,000. It's going to be, I don't know, maybe 1,100. I don't know. I got to work it out. I can't handle exponents. I don't think very many people can, you know, in terms of estimation. So 27.641 divided by the 8.958. There's that number that Will was talking about. Now we go 10 raised to that. 1,217.9. Now, I mean, we can't have part of, well, I guess you can have part of a butterfly if my cat's been out there, right? But the point is, again, it doesn't model nature perfectly. On an exam, you might be told the number of butterflies observed rounded to the nearest 100 is what? And you would enter 1200. Or to the nearest butterfly. Any questions with that one? All kinds of logarithmic relationships. You know, if you were to crack an egg into a pan, the white, I don't know if you've noticed this, the white has kind of two sections to it. There's the very runny part. If you've ever tried to separate whites from yolks, you'll know this. When I separate whites from yolks, I wash my hands really well, but I do it in my hand. I crack an egg and I dump it in my hand. And then I let the white run through my fingers. And the very thin part of the white goes through right away. And then there's that kind of globular kind of stuff that just kind of hangs on. Eventually it goes out. When you crack it in a pan, you'll see the white spread out, and then you'll see that inner part. It's called the albumen, I think, that's there. And there's a relationship between the height of that albumen and the number of milligrams of cholesterol in the egg. And it's almost precise that if you measure the height in millimeters and you put it into this formula, and it's a logarithmic formula, you will get the number of milligrams of cholesterol. And there's another one for the number of milligrams of protein based on the height of that albumen. There's logarithmic relationships between what's called the metabolic rate of, say, a jackrabbit and its mass. There's biological applications to logarithms. Anyway, there are a whole slew of problems for you to practice here. 1, 5, 6, 10, and 14 are dealing mainly with today. But on page 28, that whole page is logarithmic practice. And for what we're going to move on to tomorrow, you need to be solid with your understanding of logarithms. Graphs, yeah, they're important. Applications, yes, they're important, but not nearly as important as your knowledge of logarithms, because without that, everything else is a chore. So get to work on that, please.